Okay guys, today we're going to talk about the unit function, and it's going to be a short video because there's only 3 small problems we're going to solve using the unit function. So this is what it looks like. It's just a very simple function that goes from negative infinity to infinity, and it has a value of 1 for all positive numbers and 0 for negative numbers. However, you can shift this function around, you can reverse it, you could apply all the function transformations. So we're going to see how to solve some problems using function transformations on the unit function. Alright, let's suppose we have this function x of t, and we want to find x of t in terms of u of t. So we should have x of t equals some u of t, maybe with a shift, maybe with negative, whatever transformations. It could be multiple unit step functions. The easy way to identify it is just look at the different shapes. So the first one we have is just a linear function. So this is going to be u1, okay? The second one we have is another linear function, but this one is negative. So this is going to be u2. And the last one we have is just a sort of like rectangular function that looks like this, and that's going to be our u of 3. So x of t is going to be some function u1 plus u2 plus u3. Okay, but we have to find the parameters and coefficients for each unitary function. The first one, u1, goes from negative 2 to 2. Now the thing is, we need to consider the fact that it goes back down to 0. So how are we going to draw the function right here, which is t plus 2, that only goes from negative 2 to 2 and not from negative infinity to infinity? So what we have to do is we have to multiply by the unit function. The first one is going to be right here. Oh, it's going to be right here, starting at negative 2, so that all the values of the function t plus 2 that would normally go from negative infinity to infinity, if we just pick any value here, because of the unit function in green, this value is always going to be 0 in the y-axis. So it's always going to be 0 times whatever the value is here, and it's just always going to give us 0. Same thing for every y value past t equals 0. We're going to have, well, right now we have 1, so that's a problem, because now we have the function that exists from negative 2 to infinity, but we want from negative 2 to 0, so now we have to subtract u of t, which is going to be subtracting this. So we're going to do a subtraction. Okay, what this is going to result in is u1 is equal to the function t plus 2, so that's the shape of the linear function, and then times u of t plus 2. Okay, so now we have from negative 2 to infinity, but we want to stop at 2, so we're just going to do minus u of t, or stop at 0 rather. Alright, so you could see that this green function, which is the multiplication by 1, is only going to exist from negative 2 to 0, because before it would keep on going this way, but because we're subtracting by u of t, then the unit function ends at 0. And now we just repeat for u2 and u3. So I'm going to bring this up. Okay, for u2, it's very similar to u1, except we want to go from 2 to 1. This is 1. And this function is negative t plus 2. So again, now we want the function to exist between 0 and 1, so it's going to be negative t plus 2 times u of t minus u of t minus 1. And you kind of see the pattern. It's always going to be whatever the shape is. You write the function, the corresponding function, and then you write two unit functions, like a subtraction of two unit functions to essentially create the bounds for which the function will exist. If we remove this, we know u2 is going to be equal to negative t plus 2, u of t minus u of t minus 1. And now for the last function, it's kind of just a square. u3 t, we know it goes from 2 to 1, and it exists at 1, just like this, 1. Now this is just going to be a unit function that starts here, like that, and ends here, times 1. So u3 is like if we just have 1 times the bounds again, u of t minus 1 minus u of t minus 2. And that's it. So x of t is going to be the summation of all the unit functions, because it kind of applies this superposition theorem graphically, and so this will yield this graph over here, the function x of t. And that's it for this problem. Now we're going to solve some more technical problems. The previous question could be asked also from a piecewise function. Instead of giving you the graph and asking you to find x of t in terms of unit functions, they could just give you the piecewise functions and ask you to rewrite it in terms of unit functions. So it's pretty simple. Actually, I think that graphically it could be a little more challenging, because here they already give you all of the functions, and all you have to do is write the function and then times, you know, the bounds. So for example, in this case it'll be here, let's say this is going to be u1. We're going to have 4t plus 4, and then we do the bounds. So u of t plus 1, so that's a shift to the left, so it starts at negative 1, and then minus u of t plus 1 over 2. And you kind of see the pattern again, and you just sum each of them. So here it's going to be 4t squared times u of t plus 1 over 2 minus u of t minus 1 over 2. Okay, and then finally it's plus, what do we have? 4 minus 4t times u of t minus 1 over 2 minus u of t minus 1. And so there you have it. This is the function x of t. So what happens when we have the unit function inside of an integral? Well, we know that the unit function is only 1 at positive values, right? Because u of t is 1 for all values greater than 0. And so if this is going to be u of t over time, then t squared times u of t is just going to be something like this. Okay, and the important thing here is that whenever you have a unit function inside of an integral, you should always use the property to reduce the bounds. What do I mean by that? Well, at u of t, let's say we had u of t minus 1, for example, dt. Then we would have the unit function shifted at 1, and everything before 1 is just 0. And then unit function goes like this. So we would only have the points over here because all these points are multiplied by 1. So whatever values are here are always going to be multiplied by 1, but everything before 1 is going to be eliminated and just go to 0. So this integral can be reduced to 1 to 10 of t squared dt. And you should always use this property whenever you spot a unit function inside of an integral. So yeah, guys, that's it for this video. Thank you so much for watching, and I'll see you in the next one.